Sure. But if it's collapsed too far.
Welcome to a small, fertile planet. A generous planet which has always given us what we needed to survive and grow. Today, we are nearly 8 billion humans and we dream of abundance. Our use of digital and green technologies skyrockets. It devours gigantic quantities of metals. But what if we had gone too far in exploiting the Earth? At the dawn of the 21st century, scarcity is threatening. Perhaps it is time to seek our metals in space. How did we get here? Let's go back to the dawn of humanity. Man was a hunter-gatherer then, roaming vast territories. His daily life alternated between periods of scarcity and abundance. With the seasons, he found around him what he needed to survive. His impact on the Earth was insignificant.
It is part of him, in his travels, to look at what materials he could use for tool making.
At Spienne in Belgium, Helen Coley and her team are excavating the site of a major human settlement which goes back more than 10,000 years. At that time, everywhere in Europe, populations were settling down.
Spienne is one of the very large centres of flint mining which came into being during the Neolithic era. Extending across dozens and dozens of hectares, it is believed that 20,000 mining pits had to be dug there, and that it was operated for at least 1,000 years, perhaps 2,000. Settlement certainly led people to have a different relationship to resources. People will have the opportunity to dig mines and truly develop a mining craft, and also to specialize in shaping tools. This corresponds to a boom in the number of flint mines that can be found. Thus, places where, repeatedly for tens, hundreds or even thousands of years, populations returned to mine flint. Mining work is a plus. During a few months of the year, these populations dig mines, which will therefore give them the flint, with which they will shape axes, which will serve them for trade. Axes made in Spienne travelled at least 150 kilometers.
On the emerging trade routes, flint is soon replaced by metal. A new era begins. The metallurgy craft spreads and soon mines for metals make their appearance in Europe. Mining is gradually organized around a handful of metals that we have learned to work. At Salsinia, in the heart of the Black Mountains in southern France, copper and iron have been mined since Roman times. Later, Salsinia will become one of the largest gold mines in Europe.
These days, the underground mines are deeper and deeper, mechanized, robotic, air-conditioned. There is no doubt tomorrow we will exploit underwater resources, and then after that, perhaps space.
Philip Bewicks is an engineer. He is a specialist in metals and the author of several books on environmental issues.
In the 17th, 18th century, there are several advances. First, we will theorize that technological progress makes it possible to make discoveries, and to apply these discoveries to the industrial system and production of items which allow improving the comfort and happiness of humankind. When we have progress of experimental chemistry, which allows discovery of more and more different chemical elements, and the discovery of more abundant energy, fossil fuels, coal, all these elements will enable entering the 19th century using a number of new, different metals. We will have zinc, aluminum, nickel,
chrome, lithium, titanium. Beginning with the Industrial Revolution, more than 20 metals are used. Mining intensifies. These new resources, far from substituting one for the others, accumulate and create new needs.
So we have about 60 different metals. Iron ore is the most used. There is well in excess of 1 billion tons of annual production. Then there are some metals such as precious metals, gold, platinum, which can drop to a few hundred tons per year. And it is therefore this whole range of products that we will actually use for transport, cars, infrastructure, and then all our everyday objects that range from toothpaste or sunscreens to electronic products, which can contain 30 or 40 different metals.
1.4 billion smartphones were sold in 2018. The latest smartphones contains a complex mix of metals, most of which are rare metals. Indium for the touchscreen, cobalt for the battery, neodymium for the vibrator. Thanks to these, our smartphones are lighter and lighter, more and more powerful.
Rare metals created the digital revolution, and at the same time, they accelerated it. They both created and followed it.
Guillaume Pitron is a journalist and producer. He travels the world investigating the environmental impacts linked to the mining of rare metals.
You have a multiplication of uses of rare metals which takes place over 70, 80 years, because we can't do without them, given their catalytic, optical, and magnetic properties. We have rare metals in Europe. Basically, these mines, they're very dirty, and so there was a transfer of the production of these rare metals between rich countries, which didn't want the pollution generated by these raw materials, and the poor countries, which were ready to assume the Western costs, provided that they could catch up with their industrial lag. So today, the supply of rare metals to Western states is totally dependent on foreign countries, and more precisely, on China. What I've seen with my own eyes, these are absolutely colossal environmental disasters. You have near Batu a gigantic lake of toxic discharges, which is as big as Lake Geneva, and in which all the wastewater from the rare earth refining process is discharged. You have radioactivity, you have cancer villages, you have various cases of disease which are documented and indisputable. So that's the reality of rare metals.
At Salsinia, the reality is managing the consequences of 200 years of intensive exploitation. The mine closed its doors in 2004, leaving the entire region polluted for thousands of years. Here, as in all developed countries, we are trying to build a cleaner world.
Now we're moving to a new generation of energy technology, the so-called green technologies, solar panels, wind turbines, electric cars, for which metals are needed. Not just rare metals, but metals in general. We are in a complete headlong rush. We are in a world where we are 7.5 billion. We will be 10 or 11 billion by the end of the century. And these 11 billion individuals will consume more and more digital technology and more green technology. It is necessary to be aware that just for our metals needs, all technologies combined, in the next 35 years, we will consume more than everything we have consumed in metals for 70,000 years.
Pollution, exponential growth, embargoes which threaten to suffocate Western countries, the challenges ahead at the start of the 21st century are enormous. We must find new resources, new territories to exploit.
I come from Scotland, which is a traditional mining country. I come from a mining town, which has no mines anymore. We are the first generation that can look at the planets and can look at the stars and say, we can go there, we can do that. We can touch the stars, we can touch the planets.
Mitch Hunter-Scullion is just 23 years old. After brilliant studies in international trade, he founded the Asteroid Mining Corporation in Liverpool in the UK. We are still far from a multinational, some collaborators in Europe, offices rented as needed. What Mitch Hunter-Scullion has for sale is a project.
We are on a planet which is 36,000 kilometres in diameter, and we are in a position whereby those resources with a growing population are rapidly depleting. The inner solar system can provide all the resources that our society needs to grow exponentially for at least 100 years. You can find almost every resource you can find on Earth on an asteroid, just in varying quantities. To give you some approximate figures, all the mines on Earth currently mine 200 tons of platinum. On a single 1 kilometre diameter asteroid of a metallic composition, we can reasonably expect to find at least 100,000 tons of platinum per asteroid. So you're in a position where one asteroid can provide more platinum and gold than every mine in human history combined.
Deep Space Industries.
Mitch Hunter-Scullion is not the first to bet on space resources. In 2012, Deep Space Industries and Planetary Resources made their appearance with great publicity.
Ladies and gentlemen, Dr. Peter Diamandis.
Seattle, April 2012.
The vision of Planetary Resources is to make the resources of space available to humanity both in space and here on Earth. The Earth is feeling a resource pinch, and ultimately, we have the ability to turn that which is scarce into abundant, and so now is the time that we need it most.
These two American companies were created through major fundraising from large private donors.
We also have been fortunate enough to include in our company two of the key people at Google. So we have Larry Page from Google, Eric Schmidt from Google.
This is smart money investing in one of the largest commercial opportunities ever, going to space to gain resources for the benefit of humanity.
These new actors flaunt the financial means that live up to their ambitions. It doesn't take more for the blogosphere to get carried away. Until recently in the history of astronomy, the existence of asteroids was unknown. Yet without knowing it, we have always encountered them thanks to their fragments that fall to Earth, meteorites.
When you look at the sky, you don't see stones. So getting used to the idea that stones could fall from the sky was a long journey that culminated in the late 18th century.
Mathieu Gournel is a professor at the National Museum of Natural History in Paris. He is responsible for the conservation of the French meteorite collection.
All through the 17th and 18th century, there was the idea that meteorites were maybe thunderstones or lightning stones. And there was also a school that admitted that the stones could fall from the sky, but couldn't think beyond the atmosphere.
In 1794, the first to talk about a possible origin outside the atmosphere was Ernst Chladni, a German mathematician. Little by little, the entire scientific community accepted the idea that meteorites come from rock bodies which travel in the solar system. In 1801, Giuseppe Piazzi, an Italian astronomer, mapped the stars. On the 24th of January, he detected the shadow of a planet whose specific calculations had predicted its existence between Mars and Jupiter. In fact, he had just discovered Ceres, the largest asteroid in the solar system. Then discoveries followed: Pallas, Junon, and Vesta. In 1868, 100 were detected. Today, we identify nearly 1 million asteroids which orbit between Mars and Jupiter in a zone called the asteroid belt.
If I were Han Solo in my Millennium Falcon in Star Wars and wanted to cross the asteroid belt, I would do it blind. Because even if they were very numerous, they are small in a space which is infinitely large. The probability of encountering one by chance, even if they were very numerous, still remains very low.
Patrick Michel is an astrophysicist at the Nice Observatory. He is an asteroid specialist who participates in the largest solar system exploration missions of NASA and large space agencies. In 2012, Planetary Resources called on him to join their team of top-flight consultants.
Asteroids contain resources similar to what is found on Earth, because in fact they are the remains of the building blocks which formed the Earth and other planets. In the beginning, our solar system 4.567 billion years ago was a disk of gas and dust which encircled the Sun. Then this dust began to come together in clumps to bind, to form planetary embryos, and some of them ended up as planets. But part of this material never managed to form a planet and parked itself between Mars and Jupiter in the asteroid belt.
It is probably due to the presence of nearby Jupiter, which by its gravitational force prevented these asteroids from gathering. That is to say that each time there was an attempt to unite, there was, in a way, Jupiter, which extended its gravitational hand and dispersed these asteroids which wanted to assemble.
Far from the influence of Jupiter, the billions of asteroids managed to agglomerate, and little by little the Earth was formed. As it grows, its composition changes.
All celestial bodies, asteroids, like planets, have an internal heat that comes from radioactive decay. Their temperature elevated, they melted, and when a body melts, and when this body contains rocks and metal at the same time, well, the metal, which is thicker, tends to be found at the center of the body, while the rocks will be found on the exterior.
When Earth was formed, iron has pumped out all the elements called sidrophiles, that is, the elements which have an affinity for iron. And gold, platinum, etc. are sidrophiles. Thus, all precious elements went into the core. What remains in the mantle comes from the impacts that are produced after formation of the Earth. This is called the late heavy bombardment. When we take stock of the abundance of rare metals that we have in the mantle, this can only be explained by the impacts of asteroids. When you wear a piece of jewelry, much of what you have comes from celestial matter, the asteroids.
The riches of the Earth's crust would therefore be only a tiny fraction of what can be found in the asteroid belt. By studying the characteristics of the meteorites that come from it, we are able to classify asteroids into three main types.
There are S-type objects, which are mostly silicates, rich in rocky material, refractory, formed near the Sun. There is Class C, which are carbon-type asteroids, rich in water. They are initially formed beyond Jupiter, where water is able to condense. And then there is another class, in which there are metallic objects, including Class M for metal.
They're also the rarest. Psyche is one of them, a metallic mastodon of more than 200 kilometers in diameter. It attests to intense phases of formation of the solar system. Many planetary embryos have formed. But unlike Earth, these massive bodies with iron cores did not reach a sufficient size to resist the hazards of celestial encounters. According to space miners, these fragments of metal cores would contain much higher proportions of rare metals than those found on Earth. They travel through space at more than 250 million kilometers from Earth, inaccessible. Yet that's without counting on celestial mechanics.
Between Mars and Jupiter, there are very unstable areas that, when falling into, one travels a circular path around the Sun, between Mars and Jupiter, on a lengthening trajectory. And by lengthening, the minimum distance to the Sun diminishes, and thus it can intersect with the Earth. And some of them are more accessible than the Moon in terms of thrust that is necessary to supply from the Earth to reach them.
These asteroids, which sometimes pass very close to our planet, are near-Earth objects. They number more than 20,000. They represent a main target for space miners.
Asteroid Mining Corporation is developing a roadmap to the utilisation of space resources. We're looking to prospect, explore and extract materials from asteroids. Our first project is to essentially create a database of 50,000 asteroids.
This type of database already exists. Asterank is the most famous among them. The figures found there make the head spin, but for the most part they are only estimated according to the type and size of the asteroids observed. To accurately determine the resources of the solar system, space miners develop their own observation tools. For this, Mitch Hunter-Scullion is associated with the prestigious Liverpool John Moores University. Professor Ian Steele is an astronomer, a specialist in meteorite studies through spectroscopy.
Spectroscopy is simply the process of splitting light into its colours. It takes the light, and rather than passing it through a drop of water like we have in a rainbow, we pass it through a piece of glass. So either a prism or a grating, which has lots of lines ruled on it, and that does the same action. It splits the light into its different colours so we can observe it. If we just look at something like the sun, that has all the colours of the rainbow in it, because the sun is made of lots of different gases. If we look at the spectrum of a single element, like neon or argon, then we just get a few different colours. We get like a fingerprint of patterns of different wavelengths of light, different colours of light, which is unique to that element. Spectroscopy, in theory, can determine any element, because all the elements have their own different chemical signatures and all their own different patterns of light. Asteroids are a long way away in space, so obviously we can't sample them directly. So instead we have to look at the light of the bits of asteroid, which we call meteorites, that have fallen to the ground on Earth.
By comparing the light spectrum of the meteorite with the asteroid's one he observes from Earth, Professor Steele combines their respective spectra and manages to estimate the composition of each asteroid. But this observation from Earth is not easy.
The light from them is very faint. We need the biggest telescope to observe them to collect as much light as possible, and that makes it more precise, but it will still never be as good as we can record here on the laboratory on the Earth. Around the Earth, we obviously have no atmosphere around us, so there's nothing blocking the different wavelengths of light, so we can make a more fine discrimination between different types of asteroids. Because remember, what we're trying to do here is not necessarily just find asteroids that have iron in them, we want to find asteroids that have platinum group and rare earth metals. The signatures are much more subtle. So the challenge with the project that we want to do with AMC is taking the spectrographs that we've built for telescopes on the Earth. So we operate a telescope out in La Palma, a big 2-metre telescope that weighs 20 tonnes and has a spectrograph on it that weighs 10 kilograms. What we've got to do is try and miniaturise that down into something that will fit in a CubeSat that's only the size of a cereal packet and must only weigh a few kilograms.
I'm ready. I'm also ready. Wait a minute. Let me readjust GoPro.
CubeSat is a new standard of miniature satellites based on 10 by 10 centimetre modules that can be assembled together. Their components are very inexpensive.
To unfasten the hook, I have positioned myself. This is Sergey.
The other advantage is that their small size allows their deployment at lower cost.
I'm ready for launch.
They can even be launched
3,
by hand.
go.
We're very fortunate to be millennials, where we live in a society where you can gain access to satellite technology at a very, very low cost, comparatively speaking, to the space missions that went before us. So, for example, our Asteroid Prospecting Satellite 1 has a budget of €7.2 million, which is dramatically lower than any space industry would do. And we expect to launch the Asteroid Prospecting Satellite 1 in 2021.
4, 3, 2, 1, 0, plus 1, plus 2, plus 3, plus 4.
In 2018, an Indian launcher put about 100 CubeSats into orbit, among them Arcad 6, the first prospecting satellite from Planetary Resources. Arcad 6 will allow mapping of space resources. However, it must also turn its hyper-accurate sensors towards Earth and sell its data like a conventional imaging satellite. This is a way to make money quickly, for like all space miners, Planetary Resources is financially holding its breath.
There are arguably many challenges to be said. We are talking about a 10, 15, 20-year development cycle to see the industry to maturity. Our first phase, our prospecting phase, is the most economically important for us, purely because if you want to develop an asteroid mining industry, you have to be able to sustain yourself through the development of that technology. And to do that, you need to be able to provide an economic incentive. Our business model is based upon the metallic asteroids, which compose about 4% of all total asteroids in the solar system. They're the ones which we are most interested in from an economic perspective. So they're the ones that we would restrict supply of to our own primary customer segment. And if customers wanted to gain access to those data points, they would have to pay a huge premium to gain access to that information. We are essentially creating a market for space resources on Earth currently.
3, 4. Space miners do not all have the same business plan. For planetary resources and deep space industries, the resource may well be more valuable than platinum or rare metals.
First is water. Okay, so water in space, as you will come to learn, is perhaps the most valuable of the materials that we will use and find in space. Obviously, it's something that's critical to our life on Earth, and of course it will be critical to our life in space. But what we also need to realize is that water and its constituent elements, hydrogen and oxygen, are the most efficient forms of rocket propellant. As if we're able to successfully deploy and mine for water, we're going to create a network of propellant depots, of gas stations that literally open up the roadways to the rest of the solar system. So it's going to drastically reduce the cost of deep space exploration.
For its part, in 2016, Deep Space Industries developed Comet, a water-based space thruster. All this water can be extracted directly from the carbonaceous asteroids. We can already imagine swarms of mining probes rushing towards the riches of the asteroid belt, refueling on the way in space service stations.
What is quite fascinating in new technologies is the promise to make it touch a reality, including through virtual.
Jacques Arnoux is a PhD in science history. For 20 years, he has occupied a place that doesn't exist anywhere else. He is responsible for ethical issues at the French National Center for Space Studies.
Nature has endowed us humans with something a little strange called imagination. This capacity that we have, each of us, to project ourselves into another place, spatial or temporal. And as we share with other so-called higher animals as well, curiosity, when you combine curiosity and imagination, you explain an important part of the driving force of exploration. And it's been thousands of years that we, humans, we cross seas, we cross mountains, we cross air distances, and today space distances. And as long as we want to remain human beings, we will have to manage this mixture of fascination, and as well our ability to invent things, instruments, to go and see what is on the other side of the mountain, on the other side of the sea. Since the beginning of the 60s, space has been presented as the new frontier, unknown worlds that we must go explore. And new space takes up this kind of litany, creed, to give it a new face, new prophets, new images that are also technological. These rockets, which return to land on their launch pads, have become an almost mythical image. We are really in a recounted mythology. A mythology to be seen which is also a way of telling a story to be built. Instead of quietly waiting for the years to come to fall upon us, 2020, 2030, 2040, let's say, but I will make a future of it. That is to say, I will build it myself. They're not describing the future, they are building a slightly different present.
Reinventing the present requires a good business plan. For space miners, it's all about here and now. They must convince investors that they can open new business opportunities for them, but this time in space.
It's totally self-funded AMC through my inheritance. We had small amounts of money from the Scottish Government and a small amount of money from the UK government. So we need to raise €7.2 million over the next 6 months in order to then move on to the manufacturing of the satellite. We will be maintaining that presence within Scotland, but also adding to that by being in Luxembourg. So it's basically joining two dots together to make a straight line.
Welcome to the Grand Duchy of Luxembourg, the small country of high finance which must endlessly reinvent itself economically. Here too, they are betting on the resources of the future.
It is no longer science fiction. We are rapidly nearing the day where we will use the first space resources.
Mark Saris is the first president of the LSA, the brand new Luxembourg Space Agency.
What we mean here by space resources are the materials found on celestial objects. This can be the moon, asteroids, Mars, or other objects in the future. A company that wants to develop a new product or service, they can come see us. And if their goals are in line with the way that we want to develop the sector here in Luxembourg, it immediately opens the door to possibilities for assistance. These activities must remain sustainable and truly benefit the development of humanity in general.
In 2016, the Luxembourg government invested €25 million in capital with planetary resources. Many other startups, including deep space industries, have also set up in the Grand Duchy. Today, Mitch Hunter-Scullion comes in turn to present the Asteroid Mining Corporation project to the LSA. Business is business and the meeting remains confidential. The stakes are high for space miners because what they come looking for here is much more than money. It is the right to exploit space.
Today, all space activities are governed through international treaties. And these treaties, unfortunately, are not specific enough on what can or cannot be done with the resources found in space.
Since the 1967 International Space Treaty, space has been considered a common territory for humanity whose states cannot appropriate the resources. In 2015, the United States changed the game. They passed a law intended to boost the competitiveness of their private space sector. This law allows American citizens to appropriate space resources. In 2017, Luxembourg passed a similar law for companies based in its territory.
We wanted to be flexible and also leave the door open. Obviously, afterwards, the question of activity interference, the question of availability of surfaces which are on a celestial body. These are questions which I hope will be discussed and resolved at the international level.
In the wake of the United States and Luxembourg, many countries are interested in space resources, including China, which is developing space and is already aiming high. A new international treaty is now being worked on which will try to harmonize the ambitions of these new players. It could help much sooner than expected. The big space agencies in their own way are inaugurating phase 2 of space mining, exploration.
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
So we're currently living in an extraordinary era for asteroids, since we're fortunate to have 2 space missions that are visiting their asteroids, the NASA OSIRIS-REx mission and the JAXA Hayabusa 2 mission. What is great about asteroids is that they interest very diverse communities who have very different goals, yet in any case, for the moment, they all need the same information: what they are made of, their composition and internal structure. OSIRIS-REx, a NASA mission, well, it's not for nothing if in its acronym there is S for security, planetary defense, and R for resources. Why? Because even if it is a mission whose primary purpose is scientific, the information that it will harvest will naturally help miners and those concerned with security.
Like Patrick Michel in Nice, here in Meudon in the south of Paris, French scientists are taking part in these two international missions.
We must gladly accept all means which advance technology and science.
Maria Anatella Barucci is an astrophysicist and planetologist. She studies the chemical and physical nature of primitive bodies in the solar system.
Exploration of asteroids as mining is something that is increasingly in the air. But before proceeding to sampling of the materials, known as mining, it is really necessary to understand the composition, the mineralogy of these objects in concrete reality. You have to go there, take samples, and bring them back to Earth.
For their exploration phase, the Space Miners probes will proceed to the same approach phases.
It is essential to have a navigation camera that will give us the first images of the object and to be able to calculate an initial model of the object's shape.
The OSIRIS-REx mission is orbiting around the Bennu asteroid, and the main goal is to characterize the object. With the camera, we had a full surface characterization. There are rocks, different grain sizes, structures, craters. And so we will select several sites which have no risks for landing a few seconds. But in reality, the probe is not going to land. It will just, with its arm, alight on the asteroid. We call this touch and go. Thus, touch, take samples, and leave immediately. There is an arm with nitrogen, which is pushed along the surface, which makes the regolith move. And this regolith is lifted up.
The regolith is the thin layer of dust and rocks on the surface of the asteroid. In 2019, the Hayabusa 2 probe sent images of its two successful touch-and-go efforts on the Ryugu asteroid. In 2020, OSIRIS-REx will do the same on the Bennu asteroid. When the two probes return to Earth in 2020 and 2023, scientists hope to find barely a few hundreds of grams of samples.
Once the samples are on Earth, they can be studied for years and years. More than 50% of these samples are saved so that future generations may study them with more advanced instruments.
These two missions are technological exploits. However, the exploration phase of the Space Miners requires being even more accurate in characterizing the asteroids. They must go further, or rather deeper.
A touch-and-go mission is not going to allow you the confidence that the resources that you're looking for are within that asteroid. You have to land on the asteroid and you have to be able to take a core sample. By being able to dig into the surface of an asteroid, it basically confirms to us that the material within the asteroid is the same material which is on the surface. And that essentially validates our entire business model, that it's economically viable to go and recover material from that asteroid. The asteroid exploration probe will take a small core sample, so it's not going to be a large core sample, but it will essentially be a miniaturized version of our exploitation missions. We are going to be using space drilling technology, which already exists in a prototype phase.
This drill was developed for sampling on Mars, then adapted for drilling in Antarctica. It requires very little energy and exerts little pressure on the ground. This could well be the ideal tool for drilling in microgravity.
We are going to expand upon that technology with our partners at the University of Glasgow to get that into a position where it is ready for commercial use. As soon as we discover precious resources within an asteroid, we will immediately move to phase 3.
Space miners want to go quickly, but to explore and then mine asteroids, their craft will have to land on the surface. Here at Issassaparo near Toulouse, Naomi Murdoch studies the interactions between space instrumentation and the surface of celestial bodies.
On an asteroid, we're in low gravity conditions. Things don't necessarily behave in the same way as they do on Earth.
Naomi is a planetary science researcher. She has participated in many international missions, including the InSight mission to Mars. She has also been a consultant for planetary resources.
One of the challenges about interacting with asteroids is that the gravity is not necessarily constant across their surface. So what that means is there might be some regions of the asteroid where you're lighter and other regions where you would be heavier. On some asteroids, there's even the possibility that around the equator, because they're spinning very fast, the centrifugal force actually balances out the gravity. We have evidence that the surface material is moving across the surfaces of these bodies. There are avalanches on these bodies. We're going to need to understand how a spacecraft will interact with the surface. So here at Issassaparo, we've taken an existing drop tower that was used for crash tests, and we've rigged it up with a system of pulleys and counterweights. You have a box and you let it fall. Inside that box, we can have small amounts of gravity. So we take a projectile and we let it go. And we're going to have very low velocity collisions in low gravity conditions, very similar to what we're going to have on a small body.
These tests helped prepare the deployment of Mascot, one of the 3 small landers dropped on the surface of Ryugu. Craft weighing just a few pounds, designed to bounce, then stabilize. A mining probe will have to land in a specific location.
So one of the ways that people have thought about landing and attaching to asteroids is to land on the asteroid and really to anchor into the surface. One of the problems with that is that if we are attached only to the surface material itself, that surface material is not attached necessarily to the consolidated material underneath. So if this material starts to lift up, then our spacecraft is also going to lift up. So it's very, very challenging to come up with the perfect solution for how to land on the surface, attach to the surface, and stay there.
Thus, there are 2 choices. We wait to have more overall knowledge of the asteroids in such a way that our hypotheses begin to be a little more accurate than they are now, or we send a mission to first go and visit the asteroid we want to mine. We study and understand it, and we visit it back later with the right tools to be able to mine it. There's a problem with this, which is that the asteroid revolves around the sun, and just because it's accessible at a given point doesn't mean that 6 months later it still is. We have launch windows. Thus, this makes things a little complicated, but that would be ideal.
Space miners had another idea borrowed from NASA scientists. Quite simply, capture an asteroid, then bring it back to Earth.
This is extremely complicated because they are generally, for the small ones, aggregates, like a bunch of rocks which are linked to each other by their own attraction, even if it is weak. It is enough for them to stay like that, agglomerated. This is known as rubble piles. So that means that if I want to capture it, we will have to slow down its rotation. Slowing down its rotation when a body sometimes rotates itself in less than a minute, you have to control it. Maybe it has very little cohesion, and by doing that, it will scatter. You have to put it in a huge sack. The methods are very complicated.
Where we'd be capturing small asteroids in their totality and be turning them into perhaps a lunar orbit. The Moon, fortunately, is in a relatively fixed position compared to the Earth, so by putting an asteroid into a lunar orbit, you essentially create a moon of the Moon, which everybody's quite excited by, and it allows you to be 3 days travel time away from your asteroid mine.
talking with industries that want to mine, the idea isn't to discourage them, but at the same time, I am a scientist, I'm honest. I want to inform them of the complexity. So the idea has changed. Instead of bringing the materials to Earth for mining them on Earth, well, we came to the conclusion that it was still sensible to mine for exploiting these objects where they are and use them as resources to go further. And then manufacture on the spot, for example, its fuel, and see whether there are other elements that we would need, etc.
If the prospect of further exploration interests the scientific world, it is difficult to convince private investors. In September 2018, Planetary Resources went bankrupt, a write-off of 13.7 million euros for Luxembourg. A few months later, Deep Space Industries was bought by Bradford Space, an international company specializing in the manufacture of space systems. What interests them is water-based propulsion for limited use in Earth orbit. The mining of asteroids seems to have been put on hold. In order for it to take off, a link is missing between Earth and deep space, a link between the short and long term. One man has understood this well. He is both a new space prophet and a logistics titan. He alone invests $1 billion a year in his space projects.
Let me show you something.
Washington, 9th of May 2019.
This is Blue Moon. We've been working on this lander for 3 years. It'll soft land in precise way, 3.6 metric tons onto the lunar surface. It's time to go back to the moon, this time to stay. There are thousands of creative people coming up with new ideas about how to use space. But those entrepreneurial companies cannot exist today. And the reason is the price of admission to do interesting things in space right now is just too high because there's no infrastructure. When we have that infrastructure in place for the future space entrepreneurs, you will see amazing things happen. And one of the things that we have to do is inspire those future generations.
Humans think in very short time scales. Humans think in terms of 10 years as being a long time, 50 years as being a lifetime, and 100 years as being inconceivable. But 100 years is not a long time. If you're talking about the history of an Earth, 100 years is a nanosecond. We can do great things in our lifetime. So when people say you're a dreamer, I would say they're short-sighted.
So according to our study, the mining of resources, or water on the moon, is for the next decade. And all the other types of uses we envisage that it will develop over the next 40 years or so.
Asteroids aren't science fiction. We go there. We've got spacecraft there at the moment. Look at the NASA spacecraft to Asteroid Bennu, JAXA spacecraft to Ryugu. They're there. What's science fiction, perhaps, is being able to mine them effectively. But using these asteroids as a stepping stone for humanity to get further in the solar system seems like a good way forward.
The future that I would like to see is a future where humanity is cooperating to exploit the resources of the solar system in a way that's sustainable and in a way that allows us to essentially continue to flourish scientifically as a human species, to explore the solar system.
I have no illusions about the fact that if ever one day, which I doubt, there is a real space conquest for resources, well, it will be the survival of the fittest.
So, we get to choose. Do we want stasis and rationing? Or do we want dynamism and growth? We have to use the resources of space. We must have a future for our grandchildren and their grandchildren of dynamism. We cannot let them fall prey to stasis and rationing.
Myself, I think it's terrible that there is indeed such a waste of human intelligence. We could put all this energy and intelligence at the service of a sobriety, which is not a return to the Stone Age, but which is on the contrary the fact of being able to keep all the advantages of technology, of knowledge that we've been able to acquire. Enter into a world of repairability, a world with a much stronger circular economy. We will never get to 100%. There is nothing that we can recycle 100%. But today, when you see that much of the iconic metals of new technology technologies are practically 0% recycled, there is huge progress that can be made. And then also ask the question of man's place. Each time we replace a cashier with a machine, we've replaced human labor with the inevitable consumption of resources.
What could this future look like? Where would 1 trillion humans live? This would be an incredible civilization. High-speed transport, agricultural areas, no rain, no storms, no earthquakes. Some of them would be more recreational. There'd be whole new kinds of architecture.
I find it hard to believe that we will be able, and I even wonder if it's necessary to colonize other places, because when we go to space, we realize that space is empty, that everything is very, very far, and that there are very few places that are not hostile to life like human life. There is nothing like our planet. Nothing.
Aren't we solving the problem with the exact same ways of thinking that caused it? And so the real change in mentality, the real change in thinking, is to tackle these wasteful consumption patterns that only permanently shift the problem as we need more and more technology.
Why not look elsewhere for the resources that we need? If ultimately we have learned nothing in the matter, or we refuse to learn anything, we are doomed to repeat the same system, the same mistakes. Yes, we will have a little more, and well, we will make a few more mistakes, a bit more waste. We will be more numerous. On this planet, abundance doesn't exist, and unlimited resources don't exist. We must be able to manage this better. Let's learn it quickly.